FlowFuse is changing the game, and one of the big things that we just released is native node support for MCP and ONNX. But what do these things actually do? Well, today I'm going to dive deep and show you exactly why we're so excited about these product features. So modern AI systems typically run into two big challenges. The first is one of connection. The way you improve AI systems is to connect them to resources and tools to do their work better. But how do you reliably make those connections? And how do you get the AI to understand what they actually have access to? So that's big problem one. And big problem two is making this process portable. In other words, how do you train a model and then make that accessible on different hardware, different environments, and different solutions? Now, FlowFuse's answer to both of these problems is the inclusion of MCP and ONNX support. First, let's dive into MCP. So this current wave of AI is powered by something called an LLM. LLMs are large language models, and largely they're based on a sort of predictive mathematics. They look at a massive data set and then see how likely it is that this term will appear with this other term. And in doing so, they can do a lot of reasoning and a lot of understanding about that data set and produce everything from insights to transformations. The thing is that these LLMs are only as powerful as their knowledge base, and that knowledge base is sort of a constantly shifting target. In some cases, the knowledge can be static. In other situations, that knowledge base is constantly shifting. Either way, LLMs aren't really built to natively do anything. A large language model is exactly that. It's a model. It doesn't natively have tooling to do things like API calls or database queries. And the solution up until recently has been to just build direct connections through APIs and other systems. For instance, if a user asks for X, then send them to API Y and reference data Z. But these custom integrations have often been really brittle. And over time, the amount of connections for a single system just absolutely explode. And that makes for a lot of difficulty in management, not to mention all of the resource consumption that these systems face. So MCP is an answer to this problem. What MCP stands for is Model Context Protocol. And the idea is to use this commonly agreed upon protocol to point large language models to resources and tools that they can reference. Now in 2024, it was open sourced by Anthropic, but it's not specific to just Anthropic. You can see MCPs pretty much everywhere at this point. The key to understanding this is to think about something like USB-C. USB-C acts as a universal hardware connector for everything from phones to laptops, even USB-C lights. And it basically just gives every system a way to transfer data or power a device with an agreed upon standard. The idea of MCP is kind of like that. It's a universal standard that can help models connect to tools and resources in a way that's easy to understand. So what are the key goals and principles of the MCP approach? First is interoperation and composability. MCP allows AI clients to talk to a bunch of different servers, even to talk between models. And it sort of makes everything run as a function as opposed to a discrete service. So if you create a service and you list it with your MCP server, then ChatGPT and Anthropic and really any model should be able to reference that resource regardless of what the model itself actually is. Another key point here is discoverability. Clients can query MCP servers and say, hey, what tools do I have access to and what resources can I use? And that's core to the value proposition of MCP. It's the ability to discover tools and resources, do their work more effectively and efficiently. These MCP solutions are also meant to be platform and transit agnostic, meaning that it should adopt a common standard for explaining where these resources and tools live, but should allow a whole host of transport options and interactions. So let's dive into the way that MCP works from an architectural and mechanic point of view. In essence, we have three roles. We have the host, the client, and the server. So first of all, we have the host. And the host is basically where I'm putting the model that I want to interact with. For instance, if I'm working with FlowFuse and I'm referencing an MCP node, I may be doing the model work in the host that is VS Code. Next, we have the MCP client. It's the system that implements the protocols and the framework to actually access all of these resources. For the average user, it's the one that is observably doing the work. Now, it's important to note that the MCP server is not a server in the traditional sense. What I mean by that is it's not really hosting a file for you to go see. It's not like we're talking about a web server. Instead, what it's doing is hosting a collection of links and pointers in the form of URIs that basically tell you where a resource, a function, a system, etc. actually is. And then finally, we have something called the session. Now, the session is a mechanical approach to actually making sure that the system works. And basically, each session carries its own context, its own history, and allows the LLM to work on a problem over time. Now with this in mind, you can start to see why the MCP nodes on FlowFuse are so powerful. In essence, you can put all of your resources, all of your tools, all the things that you've developed within FlowFuse, and you can surface them through an MCP server to basically anybody that can connect. And that means that you can have something like FlowFuse in the cloud, offering a ton of resources and a ton of functions regardless of what system you're using. As long as your system and model supports MCP and you can connect to the actual server, you can work with this content natively. And that's super powerful for things like factory devices or IoT systems, because you can feed all of that data into a single uniform resource and then connect any model that you want to run analytics or query the state of the system. But another huge innovation here is ONNX. So what is that and how does it relate to MCP? So when it comes to things like LLMs and machine learning, there's another problem that we haven't talked about yet. And broadly speaking, we call it fragmentation. Essentially, each model and each system has its own internal representation, its own data, its own system. And this includes everything from operators to data structures. And while there's a ton of power in training a specific model on your specific data set, what happens if you want to shift models? Now, MCP solves the access part of this. In other words, regardless of the model, if you want to access a tool or a resource, you can use MCP to do that. But there's still a big problem. Not every model is going to reference its data the same way. And so the data and the weights that you generate for a specific model may not be portable to another model. The model that you actually want to use won't be able to understand what the weights mean. And this is where ONNX comes into play. ONNX stands for Open Neural Network Exchange. Like MCP, it's an open standard format. And the idea is that you can convert any model into ONNX and represent everything in your trained data in a way that can be interoperable between models. So for instance, if you train something in, say, PyTorch, and you convert it into ONNX, you create a computation graph that then renders that data in an open format that any model can reference. And that's hugely powerful for a number of reasons, but the biggest one is that it gives you hardware agnosticism. If you create something in ONNX, you can run it on faster hardware. You can run it on very specific hardware. You can run it in models that are made for that specific problem, or you can run it in other models that maybe aren't built for your specific use case, that have one or two features that you really want to use for this data set. So what are the core components of ONNX? Well, first you have the computation graph. And the computation graph basically takes all of that data and turns it into an open standard that can be referenced by anybody. ONNX also defines a standard set of operators, things like convolution or add, that standardize the way you interact with these models. ONNX also defines some data and tensor types. So much like a programming language, you'll have some types that you can reference in the set itself. It also gives you options for metadata, which is really good for classifying and contextualizing your data set. And finally, it defines a way to do custom extensions. Custom development and integration isn't necessarily the problem. The problem is that those systems have been brittle because they've been developed in isolation. Now, FlowFuse has released a node for ONNX, and it's an incredibly powerful solution. So you can take all of the data from your system, and instead of training it on just one model and hoping that that model is good forever, you can convert it over to ONNX and reference any model. And that gives you a ton of extensibility. For instance, that data set that has all of your sensor data, you may have the initial instinct to just push that to the enterprise model that is specifically designed for industrial data. But what if you want to extend that data to something else? Let's say you want to generate text-to-speech for when you have a sensor that is at a specification value, and you want an alert to be sent to a manager's phone with an audio file that says something like, "Attention, this sensor is out of temperature spec." Now, if you're using a model that is really just built for, say, industrial analytics, you're going to run into problems because that's not what that model is built for. But if you convert your data over to ONNX, then it's portable and you can run that on anything. All of a sudden, you now have a system where you can do the analytics piece of it, but you can also feed it to text-to-speech. And that's just one example, but you can start to see how something like ONNX can enable a ton of additional functionality. Now, it's important to remember that MCP and ONNX are complementary, not competing. MCP is all about runtime connectivity. It's about how we get AI models to communicate dynamically. ONNX is all about model portability. It's about how you represent, move, and work with these computational models. It's all about the computational core itself. In a full AI application, you'll see MCP and ONNX working hand in hand. You'll see something like a custom neural net get exported to ONNX. That model then may be part of a larger agent or a pipeline. And the LLM or the higher level orchestrator will then use MCP to query databases, other systems, maybe even other ONNX models. Now, there's a lot more to be said here about risks and challenges for MCP and ONNX in terms of security, governance, all those things, but this is meant to be an introductory video. Your takeaway should be this. MCP is connective tissue. It connects all of the disparate systems in your AI stack. ONNX is more like a stem cell. It is a universal type of thing that can help all systems have a sort of standard building block. Now, FlowFuse's integration of MCP and ONNX nodes is part of our commitment to innovation in this space. Now you can have something like thousands of sensors pushing their data over MQTT, and then having all that data come into a central data store that you can use to train a model. And then that model can be made portable across a bunch of different LLMs and a bunch of different front ends. And all the tools that you build upon that model can be connected to by anything that supports MCP. It makes your data truly portable and truly extensible. Industrial and enterprise data is all about control. And with these innovations, FlowFuse has put the control directly in your hands. So that wraps up this video. I hope you're walking away with an understanding of what MCP is, what ONNX is, and what they look like on FlowFuse. Now, in the coming weeks, we're going to do some very laser-pointed content on how to work with these nodes inside FlowFuse itself. So if you liked this video, please like, comment, and subscribe so you can stay up to date on all of those developments. If you want to check out MCP and ONNX on FlowFuse, you can go get a free 14-day trial at flowfuse.com, and you can get started with building your interoperable, super-powered AI stack today. This has been Christopher Sandoval, and I'll see you in the next one.